My name is Phuong. I am the first author of the poster. Today I will be presenting my poster entitled "Application of the Quantum Neural Network to Supervised Learning Tasks in Macri." Um, Here is the whole poster, and in this poster, um, I will explore the potential of the variational quantum circuits (VQC) in the context of supervised learning, and especially the application of the uh, VQC and quantum neural network in application in the smart grid. Um, our work focus on the overcoming the challenges in implementing supervised learning and neural network in the real-world smart grid, such as managing the large amount of data, and we propose using the quantum machine learning uh, model, including the quantum neural network, to achieve the better performance. We apply our QNN model to two tasks. The first one is the quantum regression model for lithium battery uh, degradation, and the second one is the quantum classification um, quantum classification model for detecting electricity theft. So we will discuss the advantage of the QN model over traditional machine learning in the handling massive data. Or uh, uh, in RIF, so our configuration for the variational quantum circuits configuration is we use 5 qubit and the number player is 3. So as we can see, this is the iteration, the QM for classification and the QN for regression. Basically, they have the same encoding variation of quantum circuit measurement and observable. They only have a different um, loss function. So let me explain quickly what is quantum encoding. Quantum encoding is a component that's trained for convert the classical data to quantum data. Quantum data is the data in the Hieu space. Is really different from the classical data. So right now there are two popular quantum encoding is um, the angle encoding and the amplitude encoding. In our research, we use the angle encoding because it's simpler than the amplitude encoding. In the quantum circuit, they use the hyperparameter theta. So this is quite similar to the weight in the classical neural network. Right. Um, measurements. Me um, me Measurement is after we update the hyperparameter theta, so we have to measure the theta because theta is in the form of the quantum probability, and after we have the measurements, we have to convert back to the classical data, and this step uh, so we can use the classical um, mathematics. So for example, we can construct a loss function um, and based on the classical data after we convert it from the quantum data. So in classification, so we will have to um, this, uh, recognize the data point is 1 or 0. It means normal customer or the customer with fraud. In the regression, we have the prediction, and prediction have to be close to uh, the the real one, the real label one. So we try to minimize the loss function. Here's our variational one-time circuits. So this is the angle encoding. We encode the classical data into the one-time data. This is how the hyperparameter um, update the weight, right? And this is the measurement and observable. So we convert the one-time data back to the classical one. In this research, I use a Quizzes at SDK and the Quilax for the simulator and FPGS as the optimizer. But we can see that the regression um, result is very accurate. Result for the classification task, right? So first we try um, to see the pattern of abnormal customer and normal customer, and we can see that abnormal customer have very fluctuated demand demand pattern, while normal customer have very not very not more stable, right? And um, this is the summary of classification experiments, and you can see that um, the accuracy is more than the 90%. So that's a very good result compared with the classical one.